Okay, if I can have your attention. All right, so today we have a special treat. Oh, William's back, by the way. So in addition to William being back, we have another special treat. So as you know, when we have earthquakes during the course of the semester, I usually like to give you a little summary about the earthquake. And this week we're going to be talking about volcanoes. And so I thought I was talking to one of my colleagues, Professor Michael Manga, yesterday, and he was telling me about the ongoing eruption in Hawaii. So I thought it would be great to have him come and talk to you guys about the ongoing eruption in Hawaii and sort of the hazard implications and how they're trying to deal with the hazard implications. It's a little different, of course, to earthquakes because it's all happening in slow motion compared to what we think about when we talk about earthquakes occurring and the earthquake hazards. But I thought that this would be interesting, and so Michael's going to talk for a little bit about the Hawaii volcano, and of course I'll be happy to answer your questions about it. And for that matter, I think he's willing to entertain questions on any volcano around the world. You can see if you can hit one that he can't answer a question on. And when he's done that, then we'll move into the normal lecture, and obviously today is to start talking about volcanoes. So with that, I'll hand it over to Michael.
Richard didn't tell me that this was going to be recorded. So you're talking about volcanoes today. How many volcanoes are erupting right now? Thousands is one guess. Other guesses? Has anyone seen a volcano erupt today? Probably not, right? So definitely nothing close by. I'm curious, though, how many volcanoes are really erupting right now on the Earth? If you read the newspaper every morning, how often do you see stories about volcanoes erupting? Not so often, right? The answer is something like sort of 15 to 20 volcanoes are erupting at any time. Have you seen volcano stories in the news recently? Yeah, so what have you seen recently? Hawaii? Anything else? There's something similar in Japan, right? I saw a story this morning about a volcano showing signs of unrest, meaning earthquakes, extra gas coming out near Sendai, apparently 20 kilometers away from a nuclear reactor. And I don't know much more about it than that, so I haven't looked at it on a map or looked at earthquakes. Any other volcanoes in the news? You should read the newspaper. It's really good for you. Okay, so this eruption, in fact, it's impacting the small town of Pahoa. What's Pahoa famous for? I'll leave that up to you to Google what Pahoa is most famous for. It's a beautiful little town in Hawaii. The eruption began in April, and the eruption itself on Hawaii has been erupting continuously since 1983. So what's significant about this particular eruption is that the lavas are following a different path than they have been, and they're moving in a different direction down something called the East Rift Zone towards the place where people are living right now. And so like many people, I get a daily update from the U.S. Geological Survey. You probably can't read this, right? It's too small. If I do plus, is that better? Okay, so what's happening as of yesterday evening? The flow is moving 7 to 10 meters per day, right? So roughly per hour, so that's about 30 feet per hour. It's about, 510 meters from Pahoa Village Road. That's the main road that goes through the town. It's a little bit further to Highway 130, which is the main highway that gets people from the southeast of the Big Island to the biggest town of Hilo, and the flow is about 50 meters wide. So I thought I'd show you a few pictures to give you a sense of what's happening. And as Richard pointed out, this disaster is a little bit different from earthquakes, right? Earthquakes aren't predictable. Maybe Richard told you otherwise. But, and after an earthquake, of course, you deal with the aftermath. You respond to it. In this case, we've had a few months of notice that there's going to be a problem. And so all the agencies responsible for dealing with disasters have time to prepare. Hopefully they're coordinated, and hopefully they can have a thoughtful response to the disaster. Most important, since we're going to be overtaking a road, can you see Highway 130 here, is building alternative roads in Hawaii. And so the Civil Defense Agency and the local and the Department of Transportation have been resurrecting 2 roads to make them more amenable for lots of traffic. Okay, so what are we looking at on this map? Right? Highway 130. Any little box you see here is a building. This is the town of Pahoa. It's about 1,000 people. Everything in red are flows that advanced yesterday. Everything in pink are older flows. So it's not moving that fast, right? In which direction do you expect lava flows to move? Downhill, right? For anything geological, that's a really good guess. Things move downhill. On this map, they've also plotted some bluish lines that you might be able to make out. That's places where streams would tend to flow, right? And streams, water definitely flows at the lowest elevation, so downhill. Is the lava flowing completely downhill? Is it following those streams? Well, to answer that question, I guess I'm essentially asking, is this pink stuff following one of these blue dotted lines? Is it? It looks like it when it started over here, where it says narrow gully, the lava's flowing down where the river goes. Then it crosses the river and takes a different path and hops over to a different river channel. And so these types of flows are a type of flow we call pahoehoe. Maybe I'll show you in a couple minutes what these look like. For the most part, they go downhill, but they also create on their own initiative what downhill is. Right? As the lava is flowing, it's piling up material, and that material changes the slope, and it changes the direction they can flow. So these particular types of lava flows have an element to them that makes them a little bit unpredictable. For the most part, they go downhill, but they can start changing directions. Okay. Any questions about what we're seeing now? Okay. So I'm going to show you just a few pictures going back in time, and so you get a sense of perspective, and then I'll show you how these lava flows work. So here you get a slightly bigger view of the southeastern part of the Big Island of Hawaii. The Big Island of Hawaii is basically 3 big volcanoes. And one of them, where most of the activity is centered, is called Kilauea Volcano. It's actually a little bit to the left of this picture. The lava is flowing from the left to this main vent here called Pu'u'o'o. I think that's about 10 kilometers or so. And then right now it's emerging to form the pink area you see right here. And so this is the flow that started erupting in April. It's been traveling down what we call the East Rift Zone. And you can see where the town of Pahoa is. Everything in gray are flows that erupted since 1983. And since 1983, most of the lava shown in gray, right, was traveling directly to the ocean. And in fact, you can see this highway here, right, 130. It wraps around the southern part of the island and was buried by those lava flows. And there used to be a whole community of people that lived underneath those gray lava flows that were buried between 1983 and 1986. Yeah?
Why did this direction flow to the ocean?
Excellent question. So why, unlike all the previous ones, is it not continuing to flow to the ocean? And why is it going this way? So what's not easy to see on this map is the elevation of the land surface. There's basically a ridge right here. And if the lava stays on the left-hand side of the ridge, downhill is actually the direction it's flowing. And so previously the lava was flowing to the right. Yeah? So the question is, can we change the direction the lavas flow? And I'll show you a picture of how these lavas work in a second so you can get a sense of why it's complicated. In the 1980s, in fact, in Hawaii, they did try things. These lava flows make things that are sort of as tall as us and taller, and they're heavy under 2,000 degrees Fahrenheit, so 1,200 degrees Celsius. So it does like to melt things and burn things, but you can pile up other lava to try and divert it. What you can't change, and maybe you have a sense of scale, this is where the lava is now. There's a 2-mile scale bar. It's erupting from the vent. Right? So there's no way to change what's coming out of the volcano. Right? It's going to keep spewing that lava out to the surface. What you might change is where it's going over the surface. And so you might protect your house and then your neighbors get the lava. But in fact, previous attempts to divert lava flows have not been very successful. They tried this in Italy at Mount Etna. The best example where it has worked is a small island in Iceland where they cooled the lava with lots of water from the ocean. Interestingly for this disaster, there's no discussion about trying to divert the lava flow. And I think in part it's because the people who live in Hawaii wake up every day, they look outside, and what do they see? They live on lava flows and they see a volcano, right? They're built and living on top of a volcano. And they knew it was going to happen eventually. Right? I guess in Pahoa it's going to be tomorrow or the day after, but it could be 100 years from now, 30 years from now. I guess just like we're all ready for the earthquake to happen, right? We know it's going to happen eventually, and we have to accept it. So here's why this is a bit tricky. It was flowing over the surface downhill. Then the lava disappeared. It went back underground to a crack underground. And this is another aspect of these flows that make them unpredictable. It goes underground and follows underground pathways, emerges at this new location over here, and starts flowing in a different direction. And so for the U.S. Geological Survey that has to monitor this flow, right, when it first happened, I guess you would guess that this community over here, the Lani Estates, was most at risk. Then the lava flow goes underground, emerges somewhere else, and it's heading towards Pahoa. So I don't want to waste all your time because Richard has lots to tell you about cool things volcanoes do. But I'll try and give you a sense about how these flows work. Because you might wonder, how can lava travel 10, 15 kilometers and not freeze, right? It's going very slowly. We said, 30 feet in a day? Why doesn't it freeze and solidify, right? How can it travel so far? And the reason this flow can travel so far is that it creates its own pathways. It creates things called lava tubes. And a lava tube is exactly as it sounds. It's a tube filled with lava. And so maybe we can understand this by looking at this picture over here on the left, right? The lava's flowing over this landscape. The surface of the lava cools, right? The atmosphere is cold, and it solidifies. There's still hot lava underneath of it, but that lava that's hot underneath can't cool to the surface because it's got the solid crust on top of it. And maybe I'll pass around a piece of that solid crust that I just lost. And Richard will bring it back to me, right? It's a piece of this. This is a type of lava we call pahoihoi, and it's a piece of this that erupted in 2006. Okay. So once this crust forms on top, the lava underneath is still hot, and it can't cool. It's essentially being insulated. And so this allows it to travel, in this case, 10 or 15 kilometers. In other historical cases, distances of over 1,000 kilometers without cooling. And so because there's this flowing lava underneath the solidified crust, this also adds to the unpredictability, right? As this hot lava is flowing through this crust right here, sometimes it gets trapped. It can't advance any further, and it builds up pressure, and then it squeezes out the side. And so if you read carefully what the USGS said in that little announcement I got, it said that things called breakouts were happening in the last 3 kilometers of the flow. What you're looking at in this picture is an example of one of those breakouts, where lava is squeezing out the side of the flow, creating the possibility of flows that go in other directions. Okay. Maybe last 2 things to point out. In these pictures, you see lots of steam, right? The lava is 1,200 degrees Celsius. That's probably enough to ignite all the vegetation. And so there are fires that happen because of these flows. On your own initiative, you can look at the pictures that are appearing on the web. I was going to show you one last picture to show you what a lava tube looks like, because I think they had one on this website. Does it make you motion sick when I do this? It makes me motion sick. That's Tim Orr. Okay, actually, if you look carefully, you can see there's a crack right there and there's red stuff underneath. These pahoihoi flows are what we call inflated flows, right? The lava's flowing in the middle. If you were to stand there and watch, Tim Orr right there would be moving up over time, because lava's being injected and solidified, and the lava continues to be injected. And so when this flow's all done, that flow's probably going to be, 2 to 10 meters thick. It's growing from the inside out. And he's a professional, right? He's got a PhD in studying volcanoes, so I guess it's okay. It's his job. But the reality is if you're not careful, your boots will melt when you walk in these lava flows. So you want to keep moving. And if some of these pictures that did scroll by very quickly that have colors in them. Okay, here's one. The picture on the right, that's taken with something we call a thermal infrared camera. It's measuring infrared radiation, so it allows you to see temperature. And so even though that flow looks all black during the daytime, it's still hot enough to be emitting thermal radiation. So it's still plenty hot. So I think I have time to answer questions, of course, if you have any questions.
I'm interested. How many people have used Hawaii for the big island?
Yeah, way better than...
Volcano Observatory, where there's a big caldera, and then, of course, what Michael's talking about here is down to the southeast of that caldera. How many of you went and actually looked at that? Okay. Well, now is a good time to go and visit Hawaii. Go to the Big Island, and make sure you go around Highway 130 down to the southeast of the volcano. When I went, I'll tell you, when I went the first time, I went to see a friend who works at the Hawaii Volcano Observatory, so he could tell me where to go to try and see some of this lava. I walked into his office, and he handed me a metal spoon attached to the end of a metal, like a mop handle. He handed it to me and told me where to go and told me to try and scoop out lava from one of these tubes that, like Michael was talking about, which I then tried to do, but unfortunately I couldn't find any lava. So people go and they do this, and they bring home their dollops of lava, and so I think I'm encouraging you to do that, although I'm probably not supposed to. Anyway, okay, well, let's thank Michael for coming and giving us an overview. Yeah, I don't think so. Any other questions? Last chance? All right, great. Thanks, Michael. Okay, well, I'm afraid my material is nowhere near as exciting. So instead, we're going to sort of back up a little bit and talk about volcanoes more generally. Question? Yeah, you can hand in the assignments. So let me, 1 second, and I'll cover that. Okay, so let's start with some announcements. Okay. Oh, not working. All right. Okay, first of all, your second midterm is coming up. It's on Tuesday, 1 week today. It will cover material from the last midterm up until Tuesday, so it will include material from today and from Thursday. Okay? And there will be a review session that the GSIs will organize like last time, and so they will email you the details of that review session once they have it set up. The format of the exam will be exactly the same as the format as the first midterm. Okay? Any questions about the exam? Yeah. So only in the sense that it's the same sample questions. So I point here to the same sample questions, and I forget now which really shows the format of the exam. It's the same file that was there last time, and I don't remember if there were any questions specifically to this part of the course. So in a sense, I guess the answer is no. But it's the same format, the same style, etc. Okay, another question? Okay. Yes, there'll be questions on the tsunami video from last time. That's right. Okay. Other questions? Yeah, those of you, so that tsunami video, I included it because I think it gives you a real sense of sort of the scale of a big earthquake and, of course, the tsunami that was associated with it in Japan. It used to be available online. You could just watch it again online. You can't anymore, but you can buy it in the iTunes store for like $2. So there's no difficulty in watching it if you want to. Yeah. Oh, and it's been ripped, and it's been posted on YouTube as well. So if you look on YouTube, you can find it as well. Okay, any other questions about the exam? Okay, so then the other is that the assignment 3 is due today. So that's an online assignment, of course. Hopefully you've done it, because I know that people sometimes have technical difficulties, so if you've left it to the last minute, you could be in trouble. What you need to do is when you do the exercise, and then you answer some questions, and at the end you print out the little certificate, and that's what you need to hand in, and you need to hand it in by 5 p.m. today. And we'll pull up a table. We'll try and figure out a way if you can hand it in here at the end of the class, and if not, then you can put it in the mailboxes in 340. Please do not put them in my mailbox. You need to put them in the mailbox of your GSI if you take them to 340. Okay, any questions about logistics? Okay, so I have to figure out how we're going to handle time now. Okay, so today I'm going to really talk about primarily volcanoes. But the flow here is that, of course, we talked about earthquakes, we talked about large earthquakes. The NOVA video on Thursday was about the Tohoku earthquake, which was a very large earthquake and a tsunami. Today I'm primarily going to talk about volcanoes. That's why I asked Michael to come. But I want to start by kind of just pointing out the connection between these three things, volcanoes, earthquakes, and tsunamis. And so the reading for this material is chapter 9 in your textbook. So the relationships between these three, well, of course, some of them are very obvious, and some of them are less obvious. The first obvious one is the relationship between earthquakes and tsunamis. Of course, big earthquakes in subduction zones are what generate big tsunamis, as you saw with the Tohoku earthquake, and then the Sumatra earthquake on Boxing Day of 2004 was another big example. Volcanoes can actually also create tsunamis. So when you create tsunamis by essentially moving the seafloor, right? So in a big earthquake-generated tsunami, the earthquake, the subduction zone earthquake, either pushes up or pulls down a piece of the seafloor, and that pushes up or pulls down a big column of water, and that then flows out as a result of that deformation, and that is obviously a tsunami. You can also do that by having some kind of subsea landslide. So, for example, along the margins of the coast, on the continental margins, you can have landslides. So you have this big landslide beneath the sea surface that, of course, moves a big chunk of water. That can also generate a tsunami. Typically, these are smaller than the tsunami. Well, for example, the Tohoku tsunami you saw. These landslide-based tsunamis are typically quite a bit smaller. But they can be significant, and they can be associated with volcanoes. The Canary Islands is a great example of this. The Canary Islands is just offshore of West Africa. It's 5 or 6 volcanic islands, and so over time they're active today, so they continue to erupt. So each time you get one of these eruptions, you add an additional layer of lava, and obviously over time these big stacks of lava become more and more unstable. The erosion due to wave action at the sea margin continues to undercut these volcanoes, and then periodically you can have a major landslide where a sizable piece of the volcano slides off and drops down into the ocean, and that can create a sizable tsunami. In fact, a collapse of one of the Canary Island volcanoes is actually a threat to New York City, because a tsunami that these can generate are large enough, they would travel all the way across the Atlantic and they would hit the US East Coast, and there's a serious concern that tsunami would be big enough to flood much of New York, just as we've seen in Hurricane Sandy, for example, last year, 2 years ago now, flooded much of New York. A collapse of the volcano, one of the volcanoes in the Canary Islands could do something similar. So again, that's another connection between volcanoes and tsunamis. Of course, the connection between volcanoes and earthquakes is that as a volcano is erupting, as that lava makes its way up to the surface, so not the process that Michael was just talking about, of the lava basically moving across the surface, but the process of the lava moving from deep in the Earth's interior up towards the surface, that is something that takes significant time, and it generates earthquakes during the process. I'm going to show you an example of that in a few moments. Earthquakes can also generate volcanic eruptions, and this is less of a significant effect. But when you have an earthquake, you radiate out energy, you radiate out shaking. These magmas, the case of Hawaii that Michael just showed you, it's sort of very fluid, it's traveling very slowly, but it's a relatively fluid type of lava, and so it just flows. The other type of lava, which is much more sticky, can contain a large amount of gas. So if you have a magma chamber full of this lava that's full of gas, you have an earthquake, you basically are shaking the magma chamber. It's the equivalent of shaking a soda bottle, right? So when you shake a soda bottle, of course, you increase the pressure and the lid's not on well enough, it starts to squirt out the top. It's exactly the same with a magma chamber when you have a lot of gas. So that's another connection how earthquakes can actually generate volcanic eruptions, okay? So again, the point is that these processes are all related to one another, and they all happen in the same kind of environment, a same kind of tectonic environment. And what is that tectonic environment? Subduction zones, okay? So subduction zones are where you have big earthquakes, you have tsunamis being generated, and you have volcanoes, all right? They're not the only environment. You also have volcanoes along mid-ocean ridges. I'll show you that in a few moments. But subduction zones are the place where you have big volcanoes, big earthquakes, and big tsunamis. Not a good place to live. So that, of course, would apply to all of Oregon and Washington, for example. Okay? So let's... So here's a global tectonic map. It's showing the nature of the plate boundaries around the globe, along with the locations of volcanoes. Okay? So in blue are all of the subduction zones. Okay, so here we go up in Oregon and Washington. The orange color is the mid-ocean ridges. So the mid-ocean ridges, of course, are all volcanoes. Mid-ocean ridges are where you're creating new oceanic crust. How does that new oceanic crust form? Well, as you pull these plates apart, mantle material upwells, it melts, the melt comes out at the surface, so these are just long strings of volcanoes all the way along the mid-ocean ridges. So that's one type of volcano. And then these red dots are the other type of volcanoes, so that the red dots are what are called stratovolcanoes, and these are the ones that erupt in big explosive kinds of eruptions, and obviously they are directly above the subduction zone. So in South America here, the Nazca plate is subducting beneath South America, so it's dipping down to the east, and then these volcanoes